All right, so today we're doing our second day of graphing absolute value. If you pay attention very carefully on the top of our notes, we're dividing up today's work into two main parts. We're going to be analyzing a graph that's given to us and labeling all the attributes, the main range, x, y, intercepts, zeros, all that jazz. And then we're going to be talking about transformations from the original parent graph. And there's different phrases we can use to describe those transformations that we'll get to when we get to them. First thing I want to do is look at our first example. We're asked to find all the attributes, which is this left-hand column stuff we have all over here. Oops, here we go. And then we're asked to find the transformations. These are transformations. And we will identify the ones that are present and measure them as well. So our first attribute, what I'm going to do is make some key features. I'm going to go ahead and kind of make my graph a little more bold than what it is because it's kind of hard to see because it's the same exact color or I guess intensity as the rest of the lines, and it's a little hard to read some of the points. So I'm going to go ahead and just first go over that right quick. All right, the domain of this graph. How far left and how far to the right does this graph spread?
Negative infinity to positive infinity.
Negative infinity to positive infinity is correct. So when it goes in both directions, what three-word phrase describes that?
All real numbers.
All real numbers. Let's go ahead and write that phrase in for our domain. All real numbers. I'll use the hashtag or pound sign or number sign. Now the range, it definitely does not go up and down infinitely, but it will do one or the other. In this case, for range, we want to talk about the y value. Is there a lowest or highest value that it has?
Yes.
Lowest.
What is that lowest value at?
-7.
That lowest value lines up with -7 on the number line. Does the graph then grow upwards in a greater than fashion or downwards in a decreasing less than fashion?
Greater than.
Greater than. So the graph does go upwards. And does the graph actually have a point or piece of dark line at the -7 mark down here?
Yes.
Yes, so then it's actually equal to it as well. So the range is everything equal to -7 and going up or greater than -7. All right, the y-intercepts. Let's go ahead and locate anywhere this graph crosses the y-axis. So if I follow the y-axis down until I hit a point on the graph, I hit a spot right here. For reference, here's my origin. So at what coordinates do I have a y-intercept?
0, -2.
0, -2, and thank you for answering it correctly with coordinates. Questions so far on these first three lines we filled out? We're good? All right. X-intercepts, just like the y-intercepts, but with the x-axis. Now these ones, we do have two of them, and they're not on lattice intersections. They're not the easy cross points. They're like floating. So let me go ahead and zoom in, and then we're going to kind of take a class consensus about where we think they are. So from left to right, this first x-intercept, now here's 0 at the origin, -1, -1, 2, 3, 4, but it's not at 5. So where do you think we should give that point?
4.5.
Okay, so, and since it's one of 2 points, here's how we'll write it. Open a bracket because we're making a list of points. The first point on the left that we kind of agree our x-intercept is at -4.5, comma, because we do have another x-intercept. Our second x-intercept is just to the right of 0, and technically it's not right at the 1. It's a little bit before it. So give me a good estimate. It's right before.
0.8.
What? 0.5? You think it's halfway in the middle? Look at your graph. I think it's still a little closer to 1. I'm with 0.75 or +3/4. Now technically there's no exact answer because we don't know what the exact point is, but we know it's about in that range. So our x-intercepts are both at -4.5 and at 0.75. My second question here is, what's the 0? And I'm going to change this up a bit. So x-intercepts and zeros are the same thing. So is the word that we're going to write down, solution. On your exam, that's supposed to be a T by the way, not a B, solution. On your exam, you're asked the question, how many solutions does this equation have or function have? The solution just means how many times does it have an x-intercept. So for this one, how many x-intercepts do we have?
2.
So that means there's 2 solutions. And that's the most common answer. Most of our equations, when we solved them on Tuesday, gave us like a positive and a negative one, two solutions. You can have one solution, like the parent graph, crosses at the origin only and touches at one spot, that's a one solution. And you can have no solutions, where you have some graphs that are floating above and never touch the x-axis. So that, they're all possible, but the two solutions is the most typical. Now, let's continue on. Our vertex, what are the coordinates of the vertex, the point of reflection down here? What are its coordinates?
-2 and -7.
So from the origin, you say -2 left, and then -1, 2, 3, 4, 5, 6. Or am I off?
7.
Is it 7? 1, 2, 3, 4, 5. Why am I getting 6 then?
We got 7 on the ring.
Okay, then we'll go with that then. -2, -7. That's indeed right. I could be counting wrong. I swear 7 is right though. All right, and the axis of symmetry. The axis of symmetry is a line that when you graph it, let me make it a little thick. When you graph it, it actually cuts your absolute value graph right in half. And we actually did one of these last year with quadratics. We had axis of symmetry. It is always an equation, and let me explain to you how you write the equation, which is super simple. So the axis of symmetry always cuts the x-axis, so it begins with x. It's an equation, so it has an equal sign. And whatever number it touches on the x-axis is what it's equal to. Hint, hint, it's always the same number as your vertex here on the x value. So x equals -2. That's this big fat green line that I graphed. That's its equation. It's the line that cuts your absolute value graph right in half. Now, does that vertex make it a minimum or a maximum value? Minimum, because it's the bottom or lowest part of my graph. All right, so we did all the attributes. Now we're going to compare transformations. So what we need to do is on this grid, graph the parent graph from yesterday, the one that starts at the origin and goes up 1 over 1, up 1 over 1. That's right, perfectly centered and goes all nice and even. So go ahead and let's get that done really quick. The best way to do it on these grids is to make a nice solid point at your origin, maybe a big fat point, just a little thicker. And then make a point at your upper left-hand corner, upper right-hand corner, maybe one in the middle, like right here to help guide you, and then just connect your dots right through. Once you have the parent graph constructed, we're going to compare how the new graph that they gave us in black compares to the original graph in red. So for example, if I wanted to take my red graph and turn it into the one that's black already, then when I need to move the graph horizontally or sideways, did this red graph move sideways to get to where it is now? Did it move it all sideways? How many squares to the left would it have to go to line up with this vertex down here? So there is a horizontal shift of 2 units left. So if I want to turn the red graph, the parent function, into the black one, I'd first start off by horizontally shifting or moving it 2 units to the left. After it travels 2 units to the left, then where would it have to go to meet up with this vertex? 7 units down. So there will be a vertical shift of 7 units down. Now here's where our big discussion comes in. This is a total language issue. So you really have to have a grasp on what these words mean and what they're describing. First of all, I'm going to tell you that these 2 words describe the same thing, and these 2 words describe the same thing. So here's what I'm talking about. We already talked about how we can move graphs left, right, up, and down. And so what we're going to do now is talk about what compressions and stretches do. So horizontal means starting from the sides. If I stretch something from the sides, what's it going to do to that object? Make it more narrow or more wide? Just like if I vertically compress, if I took you, vertical means from the top and bottom, and I started squashing you down, would that make you more narrow or more wide? I mean, painful, yes, but it might make you for a brief second a little more wider. So these two words both mean your graph is wide or wider than the original. You guys ever watch that hydraulic press channel on YouTube?
Oh yeah.
Where they just like crush random things and watch them squish? That would be an example of a vertical compression, what a hydraulic press does. Now, if these two descriptions mean graphs get wider, then guess what these two descriptions mean? Narrower. For example, a vertical stretch means from the top and bottom, if I pull you, you're going to get more narrow, more lean, more thin. Horizontal compression is the opposite direction. From the sides, I'm going to squish you until you're more narrow, more lean, whatever. So these make your graph get more narrow. So which set of phrases describes the black graph compared to the red graph? Here's how you can measure it if you're not sure if it's wider or more narrow. You start from the vertex. You know in the parent graph, we go up 1 over 1, up 1 over 1, up 1 over 1, correct?
Yes.
For this black one down here, we had to go up 2 over 1, up 2 over 1. So is this creating a more narrow graph or a more wider graph? A more narrow graph. So these two descriptions best describe that graph in black. You can't have both descriptions. You can only be one or the other compared to the original. You can be the same as your parent function, so there's no transformation, or you can be made wider or more narrow, but you can't be both wide and narrow. Now, has this graph been reflected? Has it been flipped upside down?
No.
So don't circle it, and we'll move on. So we did the whole first graph. Any questions so far about any of the measurements, descriptions we've gotten so far? Let's apply that again now to the second one. So now we have a different type of graph, well, a different looking function. I'll go ahead and emphasize it just by kind of filling it in a little more. You can go ahead and start filling out the domain and range if you can determine it, and then I'll ask you guys for your responses right now. Give me a quick second to just fill this in. Then my origin's right here. All right. So, what is the domain of this graph? How far left and how far right does this graph go? All real numbers. It goes infinitely in both directions. What's the range? In which case, what's the lowest or highest it goes? Well, what's the lowest it goes? Infinity. Okay, so we don't write infinities for the range per se. What's the highest it goes then? It looks like it's positive 1, 2, 3, 4, 5, 6, 7. So the range, the y compared to 7, does the graph exist from the 7 and upwards in a greater than fashion or downwards in a less than fashion? Downwards in a less than fashion. And then does it exist there? Yes, we have a solid point and a solid piece of lines where they intersect, so it's equal there too. Excellent. Now let's go ahead and go on to the intercepts. What, if any, are my y-intercepts? 0, -1 looks like it is the correct one. It's right at a lattice crossing, so that's pretty easy to read. And just as annoying as the last ones, the x-intercepts aren't the prettiest. So we'll kind of come to consensus again. Here's my origin. We have an x-intercept right here, and one it looks like right here. The furthest left one, let's approximate where that is. 0, 1, -2, -3, -4, -5, -6, -7, but not -8. Let's do -7.25. I'll take both your numbers. -7 1/4. Let's just approximate. Oops, what did I do wrong about this symbol? It's supposed to be like that weird curvy little brackety thingy.
Yeah.
There we go. Symbols do matter. All right, and then what's the furthest right one? It's not quite on the 0.
That's 0.5.
You want to do -0.5?
Yeah.
All right, negative, not that it's totally that important per se, but just the idea. All right, so we know that x-intercepts and zeros and solutions are all the same things. And this one also displays how many solutions?
2.
2 solutions. All right, now to back up to a more respectable view. If it'll let me. All right. So now what is my vertex I'll need that, there you go.
Negative 4 and 7.
Negative 4, comma 7. Therefore, what is my axis of symmetry?
Negative 4.
Give me the whole equation. X equals, because it is an equation, don't forget that. And does this red graph that I filled in, or the original one on your paper, have a maximum or minimum value?
Maximum.
Maximum. All right, now let's go ahead and create the parent graph. And then we'll answer those descriptive characteristics that pertain to it. So starting from the origin, big fat point there, it's a little thicker. Go all right there. The point here, because it's a symmetric graph, it's a one-to-one graph. And right up there. It's a little jacked up on that side, but that's okay. All right, so let's answer our questions. In order to create the red graph that you see on the screen, to the purple one to the red one, was there a horizontal or sideways movement involved? Yes. How many units and in which direction?
4.
To the left.
4 units left. And then the purple vertex, after traveling 4 units to the left, would it have to have a vertical shift, an up and down movement?
Yes.
Of how many and in which direction? 7 units up. Now let's use the vertex from that red one, or the original one they gave us, and let's figure out basically what its slope is. Down 2 over 1, down 2 over 1, down 2 over 1, down 2 over 1. So, is it going to be a wide movement, or not a wide movement, a wider graph or a narrow graph? So these two choices down here best describe the transformation. And then, is it reflected? Has it been turned upside down?
Yes.
Yes, it is also a reflection. Nicely done. That, in a nutshell, is your notes for today.